I am so honored to be with you to communicate academic questions and ideas. The title of my academic presentation is Guided Crowd Evacuation Simulation by Coupling Emotional Contagion with the Perception of Evacuation Sites. I shall only take 15 minutes of your time. First of all, I want to introduce myself. I come from Hefei University of Technology, Hefei City, China. The content is listed as follows. Safety and emergency management is one of the important research topics in smart city, and the smart fire protection system is one of the important applications in the field of security. Crowd evacuation simulation can provide design, guidance, and evaluations for the system, foresee the consequences of possible fires, and optimize the effectiveness of emergency plans. Guided crowd evacuation simulation is one of the main research topics for crowd evacuation simulation. In recent years, the simulation research of crowd evacuation, based on evacuation sites, has attracted the attention of researchers from related fields at home and abroad. Some experimental study of crowd evacuation with static signature have proved that evacuation sites have a positive and significant impact on crowd evacuation. And there are many methods to simulate the guided crowd evacuation. But these methods lack of considering the influence of emotion. Compared with these methods, our method not only considers the guidance of evacuation sites, but also considers the influence of emotion. Exponential functions and linear functions are proposed to describe the relationship between viewing distance and perceiving probability of pedestrians. However, emotions are not considered in the process by which the agent perceives the emergency signs. So we use a piecewise function to calculate the perceptual probability and add the influence of emotional factors. At present, there are two types of classic models of emotional contagion. One is based on thermodynamics, and the other is based on epidemiologic models. In complex scenes, the agent will lose global information due to obstacles and virtual occlusion, and it cannot reach the final area with only one target point. In order to overcome the problem, we adopted the idea of a roadmap to add local target points in the scene and simulate the evacuation behavior of the agent through a real-time selection of these target points. The local target points are navigation points for agents in simulation. For example, this is a single-door scene with an emergency sign and an obstacle in the feature on site. We show two kinds of local target points into different features, as shown in feature A and feature B, and the navigation map composed of these two types of local target points is shown in Feature C. Agent needs to perceive evacuation signs before following the guidance of evacuation signs in the above-mentioned target point-driven approach. We use PR to represent the probability that the agent successfully perceives the information of the evacuation sign, and modified the piecewise function to generate the probability as shown in the formula on the slide. In the process of evacuation, the emotion of each agent is mainly affected by the environment and the emotional contagion. We model the emotional change in these two aspects. Since emotion is instantaneous in psychology, we use exponential function to model the emotional change of the agent under the influence of environment, as shown in the formula on the slide. We take different values for the parameters in the formula according to different local target points, as shown in the table on the slide. The emotion of the agent is not influenced by the environment, but also by the neighborhoods. Negative emotions can spread between people like infectious diseases. Close individuals tend to gather in groups, and individuals in groups are more likely to influence each other. Assuming that there are n agents, we define a matrix intimacy, which is an n-dimensional symmetric matrix. The value of each element in the matrix is between 0 and 1. As shown in the first formula on the slide, we define the social distance between agent I and agent J. Then we adopt the K-medius clustering algorithm to divide the crowd into K groups based on the social distance. Each agent has a perception radius R and detects the neighborhoods of negative emotions in the range of R. Assumed that, according to the previous algorithm, the agent finds that there are K1 neighborhoods with negative emotions in the same group, and K2 neighborhoods who are not in the same group, and the agent calculates an accumulated value of negative emotions according to the second formula on the slide. We randomly generate different ocean personality parameters for each agent and use these parameters to initialize the agent's emotional threshold. Then, according to the third formula on the slide, we will compare the emotional accumulation value with the threshold, and if it is greater than the threshold, the emotional value EM agent will be updated at the next moment. To distinguish the difference between different emotions in the simulation visualization, according to the relevant research work, we divide the agent's emotional state into 4 states, and we design different evacuation behavioral strategies for agents with different emotions. We designed the algorithm 1 for agent with positive emotion, and designed the algorithm 2 for agent with negative emotion. In the experiments, we model an exhibition scene as shown in the feature in the upper right corner of the slide. There are a door, 2 exits, and 4 emergency signs, which are represented by green balls in the scene. The exhibition wall in the scene obscures the agent's field of vision, causing the agent lose global information. In the simulation visualization, we generate 40 agents in the scene, and we select 2 agents and set them to different states. One is easy to be affected by the environment. The other is not easy to be affected. Then we circle the 2 agents and describe their trajectory, as shown in the snap feature on the slide. We can see that they have adopted different evacuation strategies for evacuation. To explore the impact of regional familiarity on evacuation, we set 50 evacuees, and the regional familiarity is set to different values for experiments, as the table above shows on the slide. To explore the impact of the number of clusters on evacuation, we adjust the number of clusters K and do experiments respectively. The experimental results are shown in the table below on the slide. We compare our method with 2 classical simulation methods, as shown in the table on the slide. In order to explore the influence of main factors on crowd evacuation, we build 2 models based on the method of this paper, which are the model with emotional contagion and the model without emotional contagion. The method with emotional contagion spends less evacuation time, as shown in feature A. Moreover, as shown in feature B, in the model with emotional contagion, the proportion of agents who perceived signs to the total number of agents decreases as the number of evacuees increases. Therefore, the method with emotional contagion has higher efficiency in crowd evacuation. This paper proposes an emotion-driven guided evacuation simulation method to better simulate the diverse evacuation behaviors of heterogeneous emotional crowds guided by evacuation signs. Thank you for listening. This is all.